Okay, hello, welcome to Calc II Recitation number 1. I'm going to be recording these for people online. Please don't do that. I said stop. Okay, hopefully that's good. Alright, here we go. So, integral is something like this, right? So it's a polynomial over another polynomial. But this one's just a monomial. This one's just x squared. So imagine if this x squared weren't here. That would be pretty easy, right? Just use a part rule, yes?
Can we expand the cube?
Absolutely, we can expand the cube. Yes, so a great way to, so let me see. Well, there's no, boom, love it. Okay, great. So, yeah, a great thing to do is expand the cube. Also, a great thing to remember is that any constant coefficients, you can just, bring those outside the integral and worry about them at the end. That's what I'll do as well. So yeah, it is definitely a good move to expand this out. Can anybody tell me what that is when you finish multiplying that whole thing out, or perhaps you have another technique to expand it out?
Q minus 1 minus 3x back to this. So 3x and after that
3x?
and then in a bracket x minus 1.
Like that?
Yeah.
Okay, that's that is correct. Why would you put it in that format?
It's a formula.
Okay, I have never seen it written that way before. In fact, okay, but what I would recommend is writing it out, fully expanded out. So in standard form where every term is separate. That's totally correct. I've never seen that format before. But yeah, like that. And remember, there's the way to figure that out is just to multiply all of these together. So FOIL everything together, and then combine like terms and so on. There's also a cleverer way to do that, which is called Binomial Theorem. But low key, that is only a shortcut. You don't even need to know about that. You can just do it the long way. That's fine. Okay, so what was the point of that? The point of that is now that this is broken up into 4 different terms, we can break the whole thing up into 4 different terms. Like this, right? This is x cubed over x squared minus 3x squared over x squared plus x over x squared minus 1 over x squared. Right, all of that dx. And that's great because each of these can be super simplified. Right, this is 7, integral from 1 to 5. Well, those cancel. That's just x. Those totally cancel. That's just 3. One of those cancels, and so 1's still left on the bottom. And then nothing you can do with that. Now, lovely thing about integration and differentiation, of course, is that you can just do it term by term. And now that it's split into these terms are all super easy to work with, right? This is just the power rule for all of these, except for that one, of course, which is the natural law. So, no problem. So here we go. Let's go ahead and take the antiderivative. This is going to be 7 times, so power rule on that, so raise the power by 1, divide by that new power. Same deal with that, raise the power by 1, divide by that new power. That's anyone other than, no. Okay. Yeah, raise the power by 1. 1 over x, that's the natural log. That's the weird exception to the power rule. And then finally, you know, you could also look at this like this, which means when you do the power rule, right, the power goes, it's very easy to mix this up with the negative power, right? But when you integrate that, the power goes up by 1, right? And then you got to divide by that new power, right? And since it was already negative, it's going to be positive now. So this is plus 1 over x, right? And you can always confirm for yourself that if you take the derivative of this, you get back to here. So there you go. And then that's that. And then I would say plus c, but this is a definite integral, so we can ignore that. We just got to do that. Right? We just got to plug in 1 and 5. So yeah. All right, so here we go. So plugging in 5. That's 7 times. Well, yeah, I'll just leave the 7 till the end. So 7 times, so plugging in 5. 1/2 times 5 squared minus 3 times 5 plus the natural log of 5 plus 1/5 minus, plugging in 1. 1/2 times 1 squared minus 3 times 1 plus the natural log of 1 plus 1 over 1. There we go. So yeah, and then just finish it up so far. Honestly, I won't, but let's just do the important things. Natural log of 5, that's some transcendental number. It's like 1 point something. So nothing you can do about that. But natural log of 1 is actually a nice integer. Does anybody know what the natural log of 1 is? Yes?
0.
That's right, because e to the 0 is 1, which is the same thing. If you just flip that around, it's the same thing as saying the natural log of 1 is 0. So yes, that term goes to 0. And then, you know, I'm sure you know how to work out the rest of it. So yeah. Yes?
I got tripped up on how you got the derivative for these. So I got the 1, like the 1/2 x squared, but then the 3x, like.
Yeah, so we were here.
Yep.
So this is good?
Yeah.
Okay, so yeah, so when you look at what the hell is the here? Yeah, right. So we're trying to get to x, right? So yeah, so the derivative of that is that, right? Because when you take the derivative, that comes down and cancels with that, you just get x. Now we're trying to find what has the derivative of 3. Well, 3x.
Yeah.
Right? Because when you do that, it goes away. It's just 3.
Is that like an exception to like the power rule? Like for example, the x, I got that because it would be x squared, and then you put the 2 below. Yeah, so it's just like you add x if it's.
Well, this is actually not an exception to the power rule. If you think about it, what we have here is 3x to the 0. And so the power rule says, leave the coefficient,
Yeah.
take this one, increase the exponent by 1,
And divide by 1.
and divide by the new exponent, right? So it's actually not an exception to the power rule. It is included in the power rule. The only one that's a the only one that's a funky exception to the power rule is this one, right? 1 over x. And the reason is because if you try to use the power rule, it says, okay, increase the exponent by 1, and then divide by that new power. Can't do that, right? So that's why this one is the weird exception. It's this other whack function out of nowhere instead. So yeah.
Can you actually also do the same thing for the 1 over x squared?
Right, so yes, so if it were -2, right? Well, now the power rule works again.
Yeah.
Right? Increase the exponent by 1, and then divide by that. Power, right? So the derivative is that. Or another way of saying it would be like that. Right? So yeah, so these are all the power rules, same power rule the whole time. There's only a single exception, which is right here, right? When the power is exactly that. Okay. Any questions on that problem? Yes.
So whenever you see like the equations and they're risen by some power, like binomials or trinomials, would it always be a good idea to expand those, or does it just depend?
It depends. It depends. It is always a good idea to think about doing that, but when it comes to integration, there is no. This is always what you should do. It really is a puzzle. Almost every time, you got to think about like, okay, well, if I did that, then it would end up looking like this, and then I'd be able to do that, but then I'd be stuck. So I won't do that. I'll do this instead. Like, you know, you kind of got to think through it like every time. So yeah, but it is very often a good idea. So always consider expanding a polynomial if you can. Okay. Anybody else on that one? All right. Does anyone else have any question that they'd like to review? So now please, the integral of 7 to yeah. No. You're good. Okay, so this is honestly kind of you gotta know it. And in this case, it was from pi over 4 to pi over 3. Right. So yeah. So let's talk about trigonometric derivatives for a second. I'm sure you know these classics. A notation that I personally use a lot is an arrow to mean derivative. All right, so just everybody's on the same page for that. I find it super useful to have such a short notation for such an important thing, rather than some ridiculous other symbol. So I'm sure you know these classics, but do you know this one? That's right, it is secant squared, which is the same as saying that. Right? And you can figure, since this is sine over cosine, you can work that out with the quotient rule yourself if you like. What about, since we just found a new one, what about that one? Does anybody know the derivative? Yeah, the derivative of.
Secant multiplied.
That's right. Yes. So it is a fact that you must know that the derivative of secant is secant multiplied by tangent, which I always find it useful. That's not true. I sometimes find it useful to think of all trig functions in terms of sine and cosine. So if you wanted to, this is also the same as sine over cosine squared. I think that's kind of an interesting comparison between these two. But anyway, that pretty much does it, doesn't it? Because we're looking for a function whose derivative is secant tangent times 7, but who cares? And here's one. You just got to know already that the derivative of secant is exactly that, secant tangent. So perfect. So this must be 7 times the antiderivative of secant tangent, which we just found is secant. So there you go. Power 3, power 4. Like that. Right? And then sure, we can work that out. That's 7 secant of pi over 3 minus 7 secant of pi over 4. And Well, you can always give it one of these. All right, here's pi over 4, pi over 3. Right. This one's right in the middle, so its sine and cosine are the same, root 2 over 2. But this one's up here a little bit, and its x-coordinate is a little, well, I didn't draw it very well. Its x-coordinate is a half, and its y-coordinate is root 3 over 2. Root 3 over 2. So secant of pi over 3, right? That's 1 over cosine. Well, cosine of pi over 3 is the x-coordinate here, 1/2. So the secant of that is the reciprocal of that. So it's not 1/2, it's 2. And something's not right.
I was gonna say, wait, how'd you get 2?
Hold on.
How did you get 2?
Hold on. Okay. Oh, it's negative. Sorry. Okay, yeah, that's fine.
Wait, what's negative?
The answer.
Yeah, but I got this one wrong. That's why I'm trying to cover it.
Oh, okay, all right. I won't look at that then. Okay, all right. So yeah. So just to be clear, so the way that you calculate secant of pi over 3 is recall that it's 1 over the cosine of pi over 3. And sine and cosine, of course, you have a button on your calculator for those. But if you want to get the precise value, you can recall the unit circle from whenever you learned about that. Right, this angle of pi over 3, if you go to that spot on the unit circle, it has these coordinates, 1/2 in the x and root 3 over 2 in the y. And so that's the same as saying that the cosine of pi over 3 is 1/2, and the sine of pi over 3 is square root of 3 over 2. So the cosine of pi over 3 is 1/2, and so which means then the secant is the reciprocal of 1/2, and that's just 2. Sweet. So the secant of pi over 3 is 2. Similarly, what's the secant of pi over 4? Well, it's the reciprocal of the cosine of pi over 4. And that's the reciprocal of root 2 over 2. In other words, 2 over the square root of 2. And there's lots of ways you can find out that that's actually the square root of 2. Let's talk about that. So the square root of 2 over 2, you can, some people say you're not allowed to have square roots in the denominator because, like, God said so or something. That's fucking bullshit. But one way that you can fix that is to, and honestly in this case it is a good idea to fix it because it's actually nicer in another format. You can give it a times 1, right? You can always multiply anything by 1. And in this case, the 1 that I'm choosing to multiply by is square root of 2 over square root of 2. And the reason I'm choosing to do that is because then the denominator is a very nice square root of 2 times the square root of 2. And the whole idea behind square roots is that that's just 2. And then the numerator is 2 root 2. And then boom, now we see that this is actually a very nice number. This is simply the square root of 2. So yeah. So in exact form, that's the answer. Well, I guess I can do a little better than that. 14 minus 7 square root of 2 is the exact answer.
What happened to the, so you had 2 over pi over 4, right? So in the and that one, right? Yeah, secant. How do you say that? Yeah, so 2 to the power of pi over 4.
I'm sorry, no, that's not.
Oh, no, that's not. That's the other thing. No, you're right. You're right.
That's a totally.
Okay.
Yeah.
Got it.
Yeah. That's my thing. Oh. So yeah. Yes.
So we should just leave the radical in our final answer? Like, that's fine to just leave it instead of trying to figure out what that is in
Well, it depends. If the question asks, give the answer in exact form, then that's that. And it's literally impossible to use a decimal to give that in exact form.
Okay.
Right? However, it looked like that question asked to give the answer to 4 decimal places.
No, I think I was supposed to write it like
It was
that.
that.
Oh, shit.
It would have taken it like that. No, it's fine.
Well,
Yeah, I
yeah.
don't think we're supposed to be using calculator, so there's no way
Yeah,
we're
we're
going
not.
to find that.
Oh, okay. Then yeah, then whatever. Then, you know, if you were doing some kind of engineering problem where you needed to know the area under this thing for whatever, then you'd use a calculator to get the thing. But if you're doing a math class where the decimal doesn't matter and you're just talking about this abstract stuff,
Concept.
then that's that. Then that's the answer, more accurate than any decimal could ever give you. You know? So yeah, that's the exact answer. Yeah. Okay. Everyone good on that? So pretty much it comes down to you gotta know. You gotta know you gotta know that the derivative of secant is secant tangent, and you just gotta know that. So yeah, so definitely remember all of those for sure. Okay. What's next? Anybody have another one? Yes.
I was wondering about this one.
Okay. x2 cubed root x plus 5 fourth root x. So it was x times 2 times the cube root of x. And sorry, was it 5 times the fourth root of x?
Yes.
dx. And were there bounds on that?
Yeah, 0 and 1.
0 to 1. Love it. Okay. So yeah, so we've got these nth roots of x, right? The cube root of x and the fourth root of x and so on. With just a little bit of rewriting, there's a way to get those to fit into the power rule.
Built in, right?
Thank you. Man, these things are escape artists. So the trick is, recall that you know, like the square root of x is another way of writing that is x to the 1/2, right? And in the same way, the 8th root of x is x to the 1/8, and so on, right? The reason that's important is because now you can use the power rule to integrate things like this, right? So all we got to do is just rewrite this using that notation. So it's x times 2 times x to the 1/3 plus 5 times x to the 1/4 dx. Now the way it's written, it's not 2 separate terms, right? If this x weren't there, then no problem. We just do this one and do that one. But there's this x outside, right? And while you can distribute the integral over addition, unfortunately you cannot, and this is very important, you cannot distribute the integral over multiplication, right? You can't just take the integral of this and take the integral of this and then multiply them together. It's not like that, unfortunately. But no problem. All we got to do in this case is just take this guy and give him a distribute, and then we're good to go, right? Because now, all right. So we'll have 2 terms. So this term, right? So this is x to the 1. If we multiply that by this, right, we would have 2 times x to the what? That's right. That's right. Yes, it is 1 or 3/3 plus 1/3. So that's absolutely right. It is 4/3, right? X to the 1 times x to the 1/3. That becomes x to the 4/3, and that's because 1 plus 1/3 is 4/3. Right? So yeah. Same deal over there. This is going to be 5x to the what? Somebody else.
5 over 4.
5/4, exactly right. Very good. Dx. Okay, cool. So now that we've done it, now that we've done that, we are good to go. This is just a power rule, right? Now it's power rule, but that's perhaps a little bit more intimidating because the powers are both fractions, but that doesn't change anything. Yes?
So when you see dx, that's the antiderivative that we're taking of that, or just the derivative?
This is kind of like one symbol.
Okay.
That means take the well, if these weren't there, this is kind of one symbol that means take the antiderivative of what's in between.
Okay. Okay.
Is kind of one way that you can think of it. But since then it also has the bounds, and I'm sure you know that that means take the antiderivative and then plug in these bounds and then subtract, right? So yeah. Okay. So yeah, so anyway, so power rule is all we need here. Just don't get intimidated by the fractions. It is all the same stuff. So let's think. So we're trying to figure out the antiderivative of this, right? Well, the 2 will just stay, of course. The power rule says take the power, increase it by 1. Right, so what's this new power after we've increased 4/3 by 1? 7/3, that's right. And then we have to divide by that power. Right, so divide by 7/3. And indeed, dividing by 7/3 is the same as multiplying by 3/7. Right? So yeah, so we're just using the power rule, right? Increase the power by 1. Divide by the new power, which in the case of fractions it might be helpful to think of that as multiply by the reciprocal of the new power. Right? Let's do the same thing for that one. 5x to the 5/4. So that 5 is going to stay. What's the new power of x here? 9/4. That's right. 5/4 plus 1. 5/4 plus 4/4 is 9/4. And then we have to divide by 9/4, or in other words, multiply by 4/9. So there you have it. So that term becomes 2 times 3/7 x to the 7/3. And then that term becomes 5 times 4/9 x to the 9/4. And then if this were indeterminate, we would have to add the plus c, but that's not going to matter because it's going to cancel out when we subtract anyway. We just got to plug in 0 and 1. And they were very nice to give us these extremely easy numbers to plug in, right? If those were other things, that would have been more difficult with those weird fractional powers. But it's just 0 and 1, so it's super easy. Plugging in 1, you get 6/7 times 1 to the 7/3. But 1 to the 7/3 is just 1, so that's great. All right, 1 to the anything is just 1, so we don't have to worry about what the powers are. And then 29ths times 1 as well, right? That's when you plug in 1. And then when you plug in 0, well, 0 to the anything is 0, so that's just 0. So it's really just that. So it's simply 6/7 plus 29ths. So yeah, so if you wanna put those together, you have to give these a common denominator. So probably I'd want to go with 63 because there's nothing better to do with that. So I'll give these both a times 9. This is 54 out of 63. And I'll give these both a times 7. That's 140 out of 63. And then you put those together, that's 194 over 63. Yes, is that correct? Hope so. All right. So yeah. So, oh wait, sorry, it wasn't. It was you. Is that correct?
I believe so, yeah.
Oh, it's everyone. Okay, cool. All right. All right. So yeah. So the whole kind of trick to that was the exponent thing, right? Realizing that nth roots can actually be written as x to the power of a fraction. And since you can do that, then you can use the power rule to handle those. So the power rule is actually very powerful because it can do any power, even fractional powers, even irrational powers if that ever Okay. Does anybody who hasn't gone yet like to offer a question? Okay, then yes.
No, it's actually not so much that.
Oh, sure.
Quick question. Do you have a set like office hours? Because I want to see some homework, but like I still kind of want to see which ones are like more complicated. I don't know if you have that.
Last semester, I'm not supposed to have office hours. I really enjoy teaching math, and I'd love to do it. But last time, I kind of overbooked my plate. I've been talking to the professor about that. I'll have to get back to you on that. I'll have to get back to you on that. I am possibly going to have additional office hours beyond this session. Yes.
All right. This is not from the quiz anymore. This is one of the topics that'll be on the test. I have everything on this homework done except for this one. I can't figure out like how to approach this because it's more of like a A and B sort of thing.
Oh, wait. Okay. 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 So we got an interesting question here. Find the integral of ax over x squared plus bx dx. So sometimes you'll be given problems where there's like extra variables, right? Where like some like numbers in the problem are actually not given to you and are instead given letters. Well, no problem. If you can figure out how to solve that, then you can figure out how to solve that. You know what I'm saying? You just gotta work this out, and then literally whatever happened to the 7 and 4, just make sure that the same thing happens to the A and B, and it'll work out after that, right? So yeah. So let's think about this one for a second. At first, I looked at this and was like, that's kind of tough. We got a first-degree polynomial over a second-degree polynomial, and this one does have multiple terms, so you can't do that same split it up thing that we did in the first problem.
You can try simplifying, right? Or I know you can.
Well, actually, yeah. But then I was like, oh, wait a second. Both these terms have at least one x in them, so you can give it one of these. And at that point, then you can give it one of these. So this just became much simpler than x plus 4. Right, so that's great. That makes it a lot easier to work. Yes?
We can put 7 outside and
That's true. Yeah, that's true. Yeah, the whatever this coefficient is, it's the same as just a 7 here, which is the same as just a 7 here. That's absolutely right.
So it'd be 1 over the over
That's
x
right.
squared. Okay.
So yeah, so the x's cancel, and so it's just 1 over x plus 4. And then, can anybody tell me the antiderivative of that?
ln x small x plus 1.
Yes. Does everybody agree with that? It is a very useful fact that if you know one function, has a certain antiderivative, well then any shift of that function, like this for example, right? So that's the same function, it's just the whole graph has been shifted to the left. Well, its antiderivative is naturally going to be that same thing, but the whole graph has been shifted to the left. So it's natural log of x plus 4. Right. So yes, that's a pretty useful trick there. So yes, this is the natural log of x plus 4. And since this was a Since this was a indefinite integral, you gotta slap on that plus c. Okay, so no problem. Let's just give this another go, right? Let's just give this a go in the general case where a and b are whatever. Well, that a, much like that 7, is just a coefficient on the whole thing, so you can just bring that whole thing outside. And then the same thing happens here on the inside. This is just x times x plus b. And then those x's, dude, I gotta do a better job keeping track of you. These x's cancel each other out. So this is the very nice a times the integral of 1 over x plus b. And then that's just this function shifted by whatever b happens to be. And so it's going to be a times the natural log of x plus b plus c. So you see, I just did an infinite family of integrals all at the same time, right? I did 5 over x squared plus 3x. I did negative 81 over x squared minus 2x. I did all of those at once. And I can tell you that all of those would be this, right? So that's the power of sort of leaving things as a variable in the meantime, working out all the calculus and so on, and then getting the answer. So now, if I were to ask you, hey, what's the integral of 14x over x squared minus 8x? Well, you should be able to instantly answer, oh, it's 14 times the natural log of x minus 8 plus c, right? Because we've already done the work for all of them, you know? So yeah, so that's what's up.
Thank you. I've been stuck on that one for a while.
Awesome.
I'm usually not the. I should probably start doing stuff like that more, where I just plug in random numbers to a and b.
Exactly.
I just struggle when I just stare at it and I see a and b. It's just like.
Exactly. Doing an example on the side where a and b are specific things is like a pro move, big time. Because then it sort of flips your brain into being like, oh my God, what? To like, oh, it's just that, you know? So like, no problem. And then you can just copy the pattern and then you're good to go. So yeah. Okay. Everybody good with that one?
Yep.
Any more? Anyone who hasn't gone yet? People in the back, yes.
I'm not sure if you guys already went over this, but I think a little bit.
Mhm.
What's this?
No, we haven't. Well, okay, so I'm going to have to ask the class for how you've worked it so far. Because as usual in math, there are many ways to solve a particular problem. That is both a blessing, but also a curse for someone in my position, because I don't know which way you guys are learning. So can you tell me, come on girl, how have you learned to handle this function, the absolute value function, right? Yes?
You can break it up from -2 to 0 and
Yes, that's right. Yeah, so the problem with this function is that it does this very unfriendly thing. Now, by unfriendly, what I mean, calculus is all about slope and continuous change and making tiny little adjustments, and everything just gradually flows. Well, that's not at all what that's doing right there. So calculus doesn't know how to handle that spot, is kind of one way of saying it. So the trick is, okay, just view this as two separate functions. Over here, right, so instead of viewing it as the absolute value of x the entire time, you can kind of view it as two separate functions. And on this side, it's the very nice function x. And on this side, it's the very nice function negative x. And as long as you separate those two sides, there's no problem. There's no problem at all. So indeed, the way that you can handle a integral like this is you can simply split it up into two integrals. One on the left side and one on the right side. On the right side, you replace the absolute value with what it is over there. And on the left side, you replace the absolute value with what it is over there. And now, these are fine, right? You just work it out like that, no problem, right? So yeah, so you kind of gotta, you kind of have to be like the babysitter almost, and like keep calculus away from those ugly spots that it's not gonna know how to handle. As long as you just, you know, say, okay, don't worry about those, I'll figure that out. You just worry about the nice continuous sections. Then it can handle it.
What you're trying to avoid is the 0 then, basically, right?
Well, yeah. Well, it's not the fact that it touches 0. The problem is that it makes a sharp turn, right? If it were here instead, the problem would be here. You know, you gotta avoid the sharp turn where the slope changes discontinuously. It makes an instant.
Oh yeah, because that's for it to apply. It has to be continuous. Is that way?
Yeah, like the machinery of calculus only works when everything is nice and smooth and everything. And so if there's a sharp corner like that, you're gonna have to like do some like surgery to kind of like, okay, you can handle this and you can handle that, but then like all figure out how to like put them back together. You know. So so that's not actually the one we're dealing with. The one that we're dealing with was, you might have to remind me. It was, I believe it was x.
Minus 4 absolute value of x.
And what were the bounds?
-2 to 1.
-2 to 1. Right. So yeah, so same kind of deal. This is going to have two different behaviors, right? Between -2 and 0, this absolute value of x is going to behave just like the function -x, right? And again, the absolute value, right, it goes like this, right? It has a slope of -1 here, so that's just like the function -x, but then it suddenly changes to a slope of +1 here, so that's just like the function x, right? So the absolute value function is kind of both of these depending on what side you're on. So since we're on the left side here, I'll replace it with what it is on the left side, which is -x. And then I also have to add the area under the right side of the curve, from 0 to 1, right? Because that's where we're going here. And on that side, I'll replace the absolute value of x with just x, because that's what it is on the right side. And now I can work these out. So that's -2 to 0 of, well, that's x plus 4x. That's 5x. And that's x minus 4x, so that's -3x. Okay? So yeah, so that's kind of the meat of it, right? Is you got to split it up there. So this is 5/2 x squared from -2 to 0. And then this is -3/2 x squared from 0 to 1. And so that's 5/2 times 0 minus 5/2 times -2 squared. Plus that. -3/2 times 1 squared minus -3/2 times 0 squared. Well, two of these guys are 0, so that's great. Don't care about that, don't care about that. And so it's just -5/2 times +4 plus -3/2 times 1. So that's great. So that's just -20/2, -10 minus 1.5. So that's -11.5. So yeah. So the key idea is if you're dealing with a function which has a weird calculus unfriendly corner to it, no problem. All you got to do is break it up into sections, and then in each section replace that function with its equivalent calculus friendly version, in each of those sections. And then you just, yourself, you just put them back together at the end. Yes.
Lot. If you get the 5x.
From here. So this was, so the left section, x minus 4 absolute value of x. Well, in the left section, that's negative x. And then if you simplify that, well, negative 4 times negative x is positive 4x. And then 1x plus 4x is 5x. So yeah. Okay. All right. That is the end of the session today. Thank you all for coming. Nice to meet you all. And I will see you next time.
So in person for foreseeable future, right?
Yeah, I will let you know if that changes, but the plan is to do these in person.
All right. Thank you.